Information about the beneficial uses of atomic energy knows no national boundaries. The facts are available today, for nuclear energy isn't waiting to help people everywhere in some brave new world of the future. The peaceful atom is here now to serve what President Eisenhower has termed the needs rather than the fears of mankind. Nuclear reactors or atomic furnaces like this one provide the product that makes possible practical applications of nuclear energy. That product is the radioisotope, the atomic tracer, a common element tagged with radiation like a sheep with a bell. And because they are tagged, they can be traced, thus giving scientists, engineers, and doctors worldwide an invaluable tool for research and money-saving applications into biology, medicine, health, agriculture, and industry. In the past 8 years, the United States has made more than 47,500 shipments of radioisotopes to more than 2,000 users in this country and almost 3,000 shipments to 53 countries all over the globe at or below cost. Today, atomic radiation controls quality of industrial production, reduces industrial costs, achieves results hitherto impossible. Radioisotopes are at work today in the oil industry. Oil producers have the difficult problem of identifying each different batch of crude oil pumped from an oil field. Therefore, a small amount of an atomic tracer is added to the head of each new batch of crude oil at the field. Pumps force the radioactively tagged oil through pipes to the refinery. A radiation counter detects the radioisotope when it arrives at the head of each new batch of oil and automatically signals refinery headquarters. Savings, $500,000 a year. And the savings increase as the radioisotope is applied to oil prospecting, leak detection, and acidizing of oil wells. But petroleum is only one industry. Let's turn to motors and see how the tagged atom works there. Piston rings, previously made radioactive in a reactor, arrive at an engineering laboratory. The lead container stops dangerous radiations. One of the rings is then attached to the piston of an automobile engine. The problem is to measure how the piston ring wears in a test engine. When the engine is running, the piston ring rubs against other metal, causing tiny particles of the ring to wear away due to friction. These radioactive particles gradually accumulate in the engine oil. By measuring the radioactivity in the oil, engineers can tell how well the piston ring resists wear. Practical applications like these are already saving more than $100 million a year in American industry alone. Back in the engineering laboratory, instruments detect and measure the radioactivity in the oil. Before radioisotopes were known, tests for wear on moving parts had to be made by slow, inaccurate methods. Atoms from the radioactive iron are disintegrating and giving off bursts of energy. A radiation counter picks up these bursts of energy and a scaler counts them. Other radiation measuring instruments work automatically. Part of the machine records radiation counts on a tape. Several dozen oil samples can be tested for radioactivity in quick succession. Automatically, each oil sample is positioned and its radioactivity is counted. Factories now have an invaluable aid in radioactivity. In any process involving sheet material, paper or metal for instance, the thickness of the product must be measured and controlled with extreme accuracy. Using radioactivity, all this can be done without stopping actual production. In the base of the thickness gauging machine is some radioactive material. The sheet product blocks some of the radiation. The thicker the material, the more particles blocked. A radiation detector counts the radioactive particles passing through the sheet material. The thickness gauge employing radioactivity thus instantly measures any variation in thickness without costly interruptions to production. Industry saves millions of dollars yearly. To find dangerous flaws in metals or to test weldings, an X-ray film is attached to the metal. Radioactive material is taken from a lead storage safe and set in place to take a picture by exposing the X-ray film. Invisible rays penetrate metal, literally see into its heart, exposing the film. Since rays pass through flaws more easily than through perfect areas, the hidden flaws or faulty weldings are pinpointed accurately when the X-ray film is developed and a picture made. The tiny radioactive source can be spotted in tight or dangerous places where bulky X-ray equipment could not be fitted. Metallurgists, engineers, and construction workers have a new partner, an inexpensive partner, in the atom. But the atom is more than a symbol. Locked in its tiny nucleus is tremendous energy. In a piece of uranium the size of a walnut, there's as much potential energy as in the amount of coal to fill a 100-car train. The question is how to get this power, how to put this vast energy to work in the power plants to run the turbines of tomorrow. Here's one way. As uranium atoms in the nuclear reactor disintegrate, tremendous amounts of heat are generated. When the heat is transferred to a liquid, and the liquid is circulated from the reactor to a boiler room, it can produce steam. Steam drives a generator to produce electricity. And we are building such a unit today, the nation's first full-scale atomic power plant to produce 60,000 kilowatts of useful electricity, enough for a small city. It won't produce power economically competitive with coal or oil, but it is a major step in that direction, a big hope for the future. The future is the child of the past. And here at the experimental breeder reactor, known as the EBR, way back in December 1951 on an isolated desert in Idaho, was produced the first useful electrical power from the atom. These very motion pictures were taken with electrical power from the EBR, the first motion picture cameras ever driven by the products of nuclear energy. The operator brings the reactor up to power to gain the high heat to be transformed to electricity. This reactor is a forerunner of the machines which one day, with the help of the International Atomic Energy Agency, may provide abundant electrical energy in the power-starved areas of the world. Electrical power from the atom, for many years, may not be economically competitive in the United States, where fuel is plentiful. But with technical help from this country, economically competitive power reactors probably could be built in a much shorter time in high power cost areas overseas. Right now, out of these first nuclear machines, we're not buying power. We're buying knowledge, knowledge that we wish to share. The United States will open a reactor training school where scientists and engineers from abroad may learn the working principles of atomic energy. Now at the EBR, tremendous heat has been generated as the controlled chain reaction reaches a critical point. Heat is used to create steam, a process monitored by a trained technician. In the control room, steam pressure is watched. When it is right, a technician in the turbo generator room opens the throttle to let steam into the turbine. The drive coupling spins. Useful electricity has been generated by the atom. The desert is dark as the control room operator gets ready to shift from standard electrical lines to electricity provided by the atomic reactor. When he shuts the switch, all facilities inside the building, such as the machine shop, and all lights outside the building will be powered by atomic energy. Today, a bold experiment. In future years, a reality for homes and factories and schools all over the world. A beacon for the future, a symbol of hope. Now to the fields and farms of the world, where the atom means more productive farming at lower cost, more and better food for a hungry world. Nuclear research is finding more effective ways of using fertilizers, is producing stronger strains of disease-resistant crops, is fighting plant pests and diseases of plants and livestock, is studying the mysterious growth process that makes the food we eat and the coal and oil we burn. Botanists at a national laboratory where crops are grown under controlled radiation conditions gather valuable data on effects of radiation on plants and on future generations of plants. This work suggests ways of developing hardier, weather and disease-resistant strains of food crops. Altered plants may produce altered seeds, a cycle that may give new types of crops to the world. Yet how nature produces the food we eat is a fascinating mystery for atomic investigation. Photosynthesis, it's called, the process plants use in taking energy from sunlight and combining it with air and soil to make the complex food elements without which no life would survive on this planet. Investigators use atomic tracers to identify the complicated compounds produced by natural photosynthesis. Knowledge from this research someday may make it possible for us to manufacture food, synthetic gasoline, and coal. In special water-cooled greenhouses, atomic researchers grow many food and medicinal plants in a radioactive atmosphere. From these plants come the many compounds familiar to medicine and biology. The crucial difference is they are radioactive. They can be traced. From poppies, tobacco, and other plants come radioactive drugs, carbohydrates, acids, proteins, vitamins that are extremely useful today to researchers in medicine, biochemistry, physiology, and agriculture. So atomic farmers harvest radioactive crops that go to work for the knowledge of man's living environment. But the most immediate benefit of atomic research to the farmer is information on the most effective use of fertilizers. Botanists blend radioactive tracers with soil in order to study soil and plant nutrition. They have already established invaluable data showing where and how fertilizers should be placed for maximum uptake, when the plant uses the fertilizers most efficiently, what fertilizers are best for various soils, and how fertilizer is absorbed from the soil. This vital information is saving thousands of tons of fertilizer and millions of dollars every year for the farmer. At the same time, research produces data that may lead to better, stronger strains of plants. Similar tracer research is giving valuable information on insecticides and making definite headway against crop pests and the diseases of fruit and shade trees. Radioaction's use for food preservation and sterilization also is being investigated. But perhaps it's the atom's fight against suffering and disease that most strongly captures our imagination. Controlled radioactivity has placed us 25 years ahead in the battle against pain and death. Capturing the atom's probing power, science has found a powerful new tool to study and defeat sickness and make a healthier, happier life for the benefit of all mankind. The versatility of the atom in medicine is illustrated by the radioactive iodine atomic cocktail, which not only speeds diagnosis of thyroid cancer and other thyroid ailments, but also is effective in treatment of some types of cancer. Iodine concentrates in the thyroid, and when it is tagged with radioactivity, it forces the thyroid to reveal its exact condition. An amazing radiation counter actually draws a picture of the thyroid area to speed diagnosis or therapy. Radioisotopes, the greatest research tool since the microscope. Cancer research goes forward all over the world with radioisotopes distributed at only 20% of cost. But cancer isn't the only disease under atomic investigation. Brain tumors, hyperthyroidism, leukemia, and other blood diseases, hardening of the arteries, heart disease, virus infections, diabetes, circulatory diseases, anemia, nervous and mental ailments. All are slowly giving up some of their intimate secrets to science with the aid of atomic energy. We go into New York's Montefiore Hospital to see a powerful aid in the fight against disease, the cobalt teletherapy unit, which was developed and is being improved by cooperating scientists all over the world. With a sharp, effective beam of atomic radiation, which does not injure healthy tissue near the cancer, the nuclear tool bombards deep-seated tumors with a stream of invisible rays, billions of particles of energy similar to X-rays, but much stronger. Tumors shrink, and cancer cells are destroyed as this one machine gives off more radiation than all the medical radium in the world. No cure-all, final results will take time to evaluate, but a big step forward in cancer treatment. In a message to the Atoms for Peace exhibit in Rome, President Eisenhower said that history will one day record as the most far-reaching physical accomplishment of the century, or even of 20 centuries, the discoveries which in recent years unlocked for the use of mankind the boundless energy of the atom, the versatile, peaceful atom that promotes agriculture, fights disease, provides valuable radioactive tracers for science and industry, that is the basis for future economical power for cities, homes, and factories. America, as President Eisenhower pointed out to the United Nations, deeply desires to join countries all over the globe in adapting the atom to the arts of peace.